Hi there, it's Xena again. It's Pop Orbital Charlie X-ray in the Netherlands. I want to talk about coax cable for MeshCore with you for a while, and because I had some conversation a while ago about coax cable for MeshCore, and I think there is some basic knowledge I can share with you about coax cable, because yeah, there are some things you can take into account to make a good selection for your coax cable. So let me just start showing what I mean. So I flip this thing down. I have some paraphernalia down here. I have, of course, Heltec V4. This is a newer variant of the Heltec V3, and is being used a lot for MeshCore or Meshtastic or Reticulum or any of these mesh networking systems. And normally these come with if you order them, they come with these small little coiled up springs antennas, and they have a small little connector on there, small connector you can see, and that fits on the board on here. You can click it on. Sometimes it's really finicky, and I call it the UFL connector, a really small connector, and there's a cable connected there to the antenna. Now, some people think maybe that's only one wire. Some people who know it a little bit more better know this is a coax cable, and we're going to talk about these coax cables a bit. We have different types of coax cable. We have these ones. This is also a coax cable here with the same kind of connector that can also fit on there, and on the side a bigger end connector for bigger antennas. And for these style of antennas, these bigger like pipe antennas. It's also for LoRa. Now we have a little step up. Then we have a standard RG58 cable over here. It have a standard thickness of about like 5 millimeters or something. And also have a SMA connector on one side, this one actually is, and a connector on the other side. But you have different variants with different types of connectors. Sometimes you have to crimp connectors on them yourselves. Don't really matter. So this is already a little thicker. Then we have a really thick one here. This is Hyperflex 10. It's actually about 10 millimeters thick. And you can see it have a thick, massive inside there and outside. So let me show what I mean with that. And I have a smaller variant of the same cable. I just put it there. This is Hyperflex 7. It's a little thinner than a 10. And it's important to watch for this coax. So why I'm doing this video? Because coax is of MeshCore is the most boring topic actually, because you just want to connect it and you want to make it work, right? You get this, you plug it in your computer, you flash it with a web flasher, and it connect this antenna on there, and it works, right? Okay. I think for MeshCore and all its mesh devices and everything that works on LoRa, in the Netherlands at least, because we are power restricted to 27 decibel milliwatt, or more commonly 500 milliwatt. So we are limited to an amount of power we put out. But the coax cable you use, so the transmission line from this side to the antenna, this is really short actually, is have a deciding factor in how much power actually is going to be put to your antenna. So let's talk about it. You will think that if you have because a small amount of power that's being transmitted, 500 milliwatts is a half a watt, it's next to nothing. You'll think that you only need a small cable, because there's not that much energy being transferred to the antenna, so you can get away with a small antenna. After all, they ship with small thin cables on there. So you think if you will want to extend your antenna, you want to make this cable or something, and you have one side you plug it in the board, and the other side you want to have your antenna on it, so you can put it on a rooftop or something. You could think, oh, I can just maybe get the same thin stuff, like about, let me get 2 meters of this thin little wire over here, and it will work fine, right? Because it doesn't need to transfer that much current. Well, the thing is, if you're working with DC, then you will be right, because then with DC direct current, if there's no frequencies going through there, then you can get away with a smaller cable, because then you just have the small ohmic losses. But we're not talking about DC, we're talking about actually higher frequencies, and then we have to deal with something that's called characteristic impedance. And I don't want to get technical about it, because I wanted to keep it basic. But let's talk a bit about what coax does, and how the thickness and the characteristics of the coax cable is the deciding factor of how much loss you have. And I will guide you through that. So for coax we have three different parts. So I put a little drawing over here somewhere. The thing is again. There we go. Okay, look, I put a drawing here of a coax cable, and if you look in the left corner of my camera, this is actually I just draw this little piece over here. Yeah, we have three different parts. We start with the core. Let me have something bigger to show and look like this. There's a nice cursor. It's actually the eraser, but okay, it doesn't really matter. You have the inner connector. There's a core. That's where your antenna signal is carrying through. And that's often, and most of the time, it's just solid copper or stranded copper, piece of copper. I look in the left corner again, I have it. There's a little solder on there, but it is normally copper. And it's nice copper because copper is strong enough and can carry a lot of energy. Then we have a shield or autoconductor. That's on the outside. So if you look again in the left corner, you see on the outside this is hairs. Well, there's also a conductor. That's for the return path or the ground path. So these two parts of your antenna cable, of your coax cable, makes your feed line. And there's also a dielectric, an insulator, and there's around it there's an insulation. So the core and the shield doesn't make electrical contact, so they are separated from each other. But the dielectric is also there because the impedance, which I was talking about, of this cable, you want this, let me get a, you want this impedance, you want on 50 ohms. And ohms, we do it with the omega sign. And impedance is Z. So you want the Z at 50 ohms. You also have, there are cables, they have a Z of 75 ohms. They also exist. And I will come to that later, but we have different types of cables. Most of the cables you buy have a characteristic impedance of 50 ohms, and some of them have 75 ohms. Like cables for television sets and radio, TV coax, radio, old-time radio coax, have these 75 ohms cable. They have a thinner inner conductor, and they work better for not load-bearing signals. So that's for if you have a digital TV and you feed it with coax, or analog TV beforehand, or analog radio with a coax cable, you feed this thing with 75 ohms of 75 ohms coax, and you can see it has often a little thinner inner conductor relative to its thickness. Okay, but we're talking about this one here, 50 ohms. So let me go back to the field view. So this Heltec board here, this have a LoRa transceiver on it, transmitter, receiver, transceiver, and it expects 50 ohms of resistance, of impedance, when it's driving its output. So its output is rated to actually drive something that has a resistive load or an impedance load of 50 ohms. So it doesn't really matter if you connect a resistor on there for 50 ohms, or that you put a feed line plus antenna with an impedance of 50 ohms on there. It seems like the same. We have also, let me show this. You also have these things. There's a dummy load. This if you want to have when you want to test RF systems, radio frequency systems, but you don't want to spit out it on the ether. You can screw this one on, and this is just a big 50 ohm resistor in there, so it can handle about 25 watts. So it warms up, so you can test your equipment without actually spitting it out. So it doesn't really matter if a cable have a characteristic impedance of 50 ohms or it's just a 50 ohms resistor on there. It doesn't really matter. This thing expects 50 ohms in the end. If it doesn't have 50 ohms on the end, then it gets reflected power back, and that can damage the final transistors on this thing. So that's why the 50 ohms cable is important. And why it's there, there's calculations for that. We don't bother that, just 50 ohms. So if you buy a cable for this thing, 50 ohms coax cable. Alright, so back to the drawing. Alright, so and this 50 ohms is, like I said, there's a calculation for it. I'll keep it brief. Is a function of the inner diameter and the outer diameter, and that's where the dielectric comes into play, because the thickness of the dielectric decides the location of the outer shielding conductor, and that together with the thickness, the diameter of the inner conductor, you have the characteristic impedance, and it has to do with the capacitance and the inductance of the cable that is in balance for a certain frequency, higher frequencies actually. Okay, all right. So why all of this is important? Now, it means that in order to have a cable of a certain impedance, it will vary in thickness if you want to have a thicker inner conductor. So I go back to the full view. So this one here, the Hyperflex 10 variant I showed, has a rather beefy thick inside. It's like really thick, like about 2 millimeters thick or something. And that means, in order to keep it at 50 ohms, it means that there need to be a little separation between the outer conductor and the inner conductor, because it's a function of both of them. And in order to keep it at 50 ohms, there need to be a thick layer of conduction insulator between them, or dielectric. That's the white part surrounding the core. So that's why this cable, the thicker the inner conductor is, automatically the thicker the whole cable is going to be, even though it doesn't really need to be that thick for like DC currents. Alright, so but every coax cable has losses, and we get going there, and we're getting a little interesting there. So I have some tabs open. Let's go to the screen there. Yes, first this little connector there, which was on this board. This is the UFL connector. This is big. It's a really small little connector, and you can see in the inside there, the middle there, is the inner conductor, and out there is an outer shield. And the shield prevents from signals from outside to have influence on the signal on the inside. So that's why it's all around, and that's why the name coax stands for coaxial. It means coaxial means like in circles around. If you see it from this axis, like from the length. Yeah. Okay. These coax have characteristics and have loss, and that's what we're going to talk about. So I was looking up for some. Yeah, this is one nice one. Common cable is RG58. This is the most common, let's say, most used reference cable, and that's this one. It's about, if you look in the left corner, it's about 5 millimeters thick. It's just standard cable. You have the 50 ohms. You have also a 75 ohms variant, but this is the 50 ohms variant, and it's being used a lot. And it has loss. So if you put like 1 watt of power in there, it is a signal, a radio signal, like in like 868, like 869 megahertz, and the other end of the cable is going to be less than 1 watt coming out. And how much is coming out depends on the cable characteristics, frequency, and you can look them up in charts. So I put up a chart here for RG58, 30 meters of this cable, and you can see on the top there, on this axis, you have the frequency in megahertz. So you can, like 868 is about here. So if you put a line from here down here. By the way, let me just make a screenshot of this thing and put it in the paint. And then we can put some drawings on there. Look at that. So this is good. So now I can make some notation on this thing. Let me get this thing. So we are about, if I put a line, I think so, we are about this here, like this from there down there. There we are. There's about 6, there's LoRa. Yeah, about there. Let me put it on top there. LoRa. My best handwriting, yes. There's a LoRa frequency, 868. And you can see if you have 30 meters of this RG58 cable, we have 2 lines. I don't know why it's 2 actually. Oh, it is the RG58 is the bottom one because I have the most loss actually. Because I know the Messi Pelosi MP is a name brand cable. It's very good actually, and RG is generic, so I know this RG is a little less. So this is the RG down here, RG58, and this is the MP Airborne 5. Okay. So you can see, and this intersection here, it has about an attenuation of about 16 decibel. How about here? So this attenuation in decibel. Decibel. I will go down there. And if we put a line from there to there, let me take nice orange from there to there. So about there. That looks nice and straight. So it's about 16 decibel. 16 dB loss, but what does that say actually? Okay. Decibel is a relative term. It's kind of, you have to remember 2 things. I think that's the best thing to do. If you have with decibel, look in the top right, I think. If you have 3 dB, let's say do a minus in this case, or let's don't do that because it's harder to do. Let's do plus. What is happening here? Let me scroll up. Yes. Okay, you have 3 dBs. Where are we? Yes, plus 3 dB means is double. Yeah. So for example, if we have 1 watt and then we do 3 dB, 3 decibel is 2 watt actually, yeah. So 1 watt plus 3 dB is 2 watt. If you have 1 volt, for example, and you add 3 dB to it, it's 2 volts. 3 dB means doubling it. So 6 dB is doubling it again, is 4 watt in this case. And there's other rule, and that says plus 10 dB is times 10. So if we have 1 watt plus 10 dB is 10 watt. So this is my best writing there in the corner there, but okay, it is how it is. Okay, so if you have 10 dB, it means times 10, or in this case divided by 10. Yes, and the 3 dB means half off, so divided by 2. And if 6 dB, divided by 2, and then divided by 2 again. So in this case, we have minus 16 dB, so we divided by 10. So, and LoRa, let's go back, is max 500 milliwatts. And it is 0.5 watts. So, if we have 30 meters of this RG58 cable, we're losing already 10 dB. So we divide it by 10. So that means I put it down there, 500 milliwatts divided by 10 is 50 milliwatts. Then we still have the 6 dB left, we need to take account for. So we divide it by 2 for 3 dB is 25. Divided by 2 again is 12.5. So 500 milliwatts minus 16 dB is 12.5 milliwatts. So that means if you these things can spit out 500 milliwatts maximum in the Netherlands, 27 dB, and you use 30 meters of this cable, you have about 400 left of this. So that no 40. I'm sorry, not 400. 40 left of it. So 39 parts is being burned up in the cable, and 1 part is going in your antenna. So you lose a lot of energy. You lose like about 40 times of your energy in this. So 30 meters of cables. So you have your LoRa node in the front of your house, and you run 30 meters of this RG58 cable to the back, to where you want to put your antenna on top of on your roof or something. Not going to work. So, and that's something you need to take into account for. That different cables have different characteristics. And this one is RG58 is just a common reference cable. I don't use it actually that much, but it's being used a lot. So if you have a meter of these things, so this is a meter, I just show you 30 meters. And the good thing about this is linearly scaled. So in this case, it was 16 dB off at 30 meters. So for example, if we had 3 meters of this cable, it will be 1.6 dB off. And then it will be divided by about 0.5 or something. A little over, I think about 20 to 30% loss you'll have for the cable. So it's still 20 to 30% loss. But now we're going to talk about these thinner ones here. This is the, so if you have if this little UVL connector here, and you want to connect it to a bigger antenna, you want to, for example, you want to do it go to BNC or something, you still need to go from this UVL connector to a BNC connector. Or what I see more often is you're going from this UVL connector to I'll drop it, to an SMA connector. SMA is being used a lot for these screw-on antennas. Let me show you one. For these type of antennas, or these kind of Wi-Fi type of antennas. You have also have them for LoRa 868, and you can just screw them on there. That's easier, but you still need to have an enclosure where you can put this one on there, and then connect this one to your LoRa board. But the RG58 has a decent loss at a certain thickness, but this one is really thin, and this will really affect your loss. So I go back to the screen and I'm gonna show you what happens there. So we back here, and we have this calculator here. I put it up, so you can calculate for different types of cables at a certain frequency. Normally you put 868 here, but we operate at 869 because that's where we can put out the 500 milliwatts. And we can put some cable type here. So I put like the RG cables here, and I put the RG174. That's a little thicker than this one. This I think is I had it somewhere. Where is it? This. It's a little thicker. It's about 2.5 millimeters thick. It's still being used a lot also. And we go see what's going to happen if we have, let's say, 3 meters of this thing, and at this frequency. So we calculate, we scroll down, and then we see attenuation is 1.3 decibel per meter. We have 3 meters of this thing, so it attenuates 3.9 decibel. So we know it's going to be at least less than half, and we can see it here. Cable run efficiency, 39.50%. That means that that more than half of your power is being burned up in the cable. So if you put out 500 milliwatts or half watt, you're going to have about 200 milliwatts actually radiated to your antenna. So you have to think about that. If you want to have long runs, you unfortunately have to go with thick cables, and it's not because of the power handling. It's because of the loss. So if we go with like LMR or something, LMR, do we have that? Like LMR 400. Let's check that. LMR 400. That's comparable to this one, to the HyperFlex 10. It's about the same quality, same characteristics. It's a thick, beefy cable. It's about a centimeter thick, and now I can show you what happens in there. So I put LMR, and I will have 3 meters of that at the same frequency. I'll calculate, and then we can compare it, and then you can see we get at least 90% we get to the antenna. So for the same 3 meters of cable, so we put 3 meters, like from your electric box to your roof. You maybe need 3 meters for your antenna. If you have put one of these up, left corner, want to put these on your roof, you need about 3 meters of cable or something. Yeah, if you can just use cheap cable like thin one. You're going to lose more than half of your power. But if you use a thicker one, like an LMR 400 or HyperFlex 10 or something, then at least 90% is going out to your antenna. So that does really affect your radiated power, and that's something they have to think about. So now we're talking about 3 meters, but some people need maybe 4 or 5 meters. If you do 5 meters, and we calculate it, it's 86. But if we let's clear this one, and then we do the RG, the thin one again, because some people think, yeah, I can just use a thin cable, right? Because there's no problem. And we do like this one, and we have 5 meters of that stuff. Yeah, a little over 20% is getting through. So you're losing almost 4/5 of your power. So if you put out 27 decibels, 500 milliwatts, only 100 milliwatts is getting to your antenna. And that means if you quadruple your power, you quadruple your range. But if you divide your power by 4, you halve your range. So normally, if you have a node, with this node here on the right side, with this cable, I can maybe reach a kilometer or something in the city center. With the other cable, you back to 500 meters with the same Meshtastic node. So that's something to take into account if you placing antenna somewhere else and you're going to use coax cable, especially for LoRa. Do this calculation. Do something like they have different calculators for different websites. You can use you can just look them up, and I call it cable loss, coax cable loss calculator, and then you can look for cables. Yeah, and cables are expensive, so you have to take that account. So if you go to like let's go for a cable like this one, this thin one here. This is thin coax cable, this is really thin stuff. It's nice because about €1 per meter, and people think, okay, I just need to carry a little bit of current, it's good, I can use it, and I run 5 meters of this thing, and I lose 80% of their power. And if you go for the HyperFlex 10, let's go for the coax. Yeah, HyperFlex 10. It costs about five times as much per meter. It's a big beefy cable. It's expensive, but as you see, it costs 5 times as much. But it is also at least 4 times better in handling the losses. So that's something to take into account. If you have short pieces of cable, it doesn't really matter that much. But if you have long pieces, like meters and up, then it's going to really be a deal breaker if you have a cable that's not suited for these frequencies. And yeah, we talked about characteristic impedance. And so we have in a graph. Let's see what I have. No thanks. This attenuation chart. Yeah. So these attenuations is like I showed earlier in this graph in the paint, is per frequency. So it's really important if you look up a cable, and these cables. This is for Messi and Poloni and P. And you can look up these charts, these attenuation charts for cable. So what you always do is you look for your length of your cable, and this time it's per 100 meters. And you look up for your frequency, so between 800 and 1000. And then you look for your losses. And this cable have per 100 meters 51 decibel of loss. So it's actually a lot of loss. I hate these virtual distance. Let's close it. And then we have the Hyperflex 5. So this RG58, and they compare it to the generic cable and their own brand cable, Airborne 5 and Hyperflex 5. Have these have comparable and better stats in these frequencies. So it's also a good thing to get name brand cables. And according to tests by other people, these figures the factories giving are quite in spec, so they're not really lying about it. So it's in spec. So, but it's something to think about. And with LoRa, you can only spit out 27 decibels in milliwatt. So that's 500 milliwatts or a half watt. So you really need to think about your coax, and it's maybe counterintuitive, but I think it's better go for a bigger, thicker cable, even though it's a small little board. And you think, you're going to have a little small board, and then you're going to run a big cable on it. Yeah, it is not really intuitive, right? You think, it's a small antenna, small power, small thin cable you need, right? But now I hope I have shown you that this beefy thick cable is actually the answer you're looking for if you want to have a antenna at a different place. So if you want your board this place and 3 meters away or on your roof or something, you want the antenna, you want to separate them. Preferably you don't want to separate them, you want them really short to each other. But sometimes you have no choice. You have your board at one place, antenna at the other place. You run a cable, go with thick cable. But you don't have to go to the Hyperflex 10. You can also go to the 7. Attenuates a little bit more. It's a little less efficient, but it's way better than the RG58, and it's especially way better than the RG174. But you have one more, and that's where it's getting really interesting. And there's RG178, and there's this one here. This is RG178, and it's thinner than the 174. It's twice as thin. And this one is where people also make a lot of mistakes, I think. What people do is they want to extend, they want to have a box, like electrical box, and they put their LoRa device in there. Just like plop in there, and they put a connector on there for the antenna, like this. And they have this. They just order them on Amazon or Ali or something or somewhere. They order these. They call pigtail connectors. And I have this RG178 wire on it, this UVL connector, and the connector of their choice, in my case, and the connector on the other side for the chassis, so they can put the antenna on top of there. So they can put it like this, and then put it outside in the box, like that. Nice, right? No long coax cable, and it works fine. But what they do, they order these things, and they come pre-made, because crimping a UVL connector on it is not really, you want to do yourself a lot. So you order just these things, you just order like this with a certain length, and order them. And these things are like maybe 20 centimeters, maybe 30 centimeters. They think, let me take a little longer because I have more space to put in my box or put around, or I can use it for a bigger box or something, You order a longer one because more space. But these things, these RG178 have extremely amount of loss. So let me look that up for you. Let's see if I can find something. First looking it up. Alright. Let's see what's the loss thing about this thing. This doesn't really say something about it. What's the loss of this thing? Typical loss varies. Oh yeah, let me put it on the screen. Oh, we're right here. Attenuation. We're right here. So we have this this cable there. So we can scroll up. This is the 178 coax. The pigtail. I don't know why they call it pigtail, because a pinky thing is small and look like tails. I don't know. This is a small cable. These are being used a lot with MeshCore, Meshtastic, because these are the ones that having the UVL connector on it. So these are being used a lot. So, and this cable, it has a lot of loss, especially if you look at here. So this is let's see how much meter we talking about here. I think this per meter. Yeah. Decibel per meter, not even per 100 meter, 1 per meter. So let me put this thing in the paint job. All right, let's put it there. Let's stretch it. Yeah, I like it. So we are, where are we? We are about here. Well, that's right on dot. There we are. LoRa. Oh, let me put a LoRa. There we are. 868. Okay. And this is our intersection. This is per meter. So if you have 1 meter of this stuff, you already have 1/2 dB loss. This is in dB. 1/2. We have loss of this stuff. That's a lot actually. So you have 2 meters of this stuff. Yeah, the half of your signal is gone already. 2 meters of this this pink stuff, the half is gone. But if you have smaller stuff, if you put like 30 centimeters, you can order them at 10 to 30 centimeters. So you have to divide it. Let me open a calculator, because hoofdrekenen is not my thing. So we have 1.5, and we do times 30 because 30 centimeters. So we have 0.45 dB loss for 30 centimeters. Okay. I need to calculate that too, because I don't know it out of my head, but it is amount of percentage. So we're going to lose something. So I asked my friend Google. Let me do this here. 0.45 dB loss. Again, Google says here about 10% reduction in power. So 30 centimeters of the stuff is going to be you're losing something. If you have the half of that, like instead of 30 centimeters of this thing, you take 15 centimeters, then we have half of it. So let's say 23. Let's round it up, doesn't really matter. So it's 5%. So instead of buying the bigger one, so instead if you go on the internet and you look for these things, pigtails for your antenna, and instead of buying the longer ones, you're buying the shorter ones, it has a difference of about 5% of your power getting through or not. That's something. That's significant. That's something you need to take into account. So that's why that's actually why I make this video, because of these things. Even 10 centimeters, 20 centimeters of this coax cable, this RG178, or thinner ones, because this was even thinner. I don't even know what it is. This one is really thin. Look, I put them there. See, the one on the bottom is even thinner than that. So the one will have way more loss at these lengths. That's why it's good that it's so short. If you have long runs of this, it's not going to work. And even tens of centimeters is going to matter. It's going to be every 15 centimeters, you're going to lose 5%. So take this short. That's why I've ordered these things. These are the 10 centimeter variants. And they come in 15 centimeters and 30 centimeters. They come. I ordered them in the 10 centimeter variant. So I have the least amount of loss because of these things. So that's something to take into account. And that's I want to talk about. So coax. There we go. So I hope it was helpful. I hope I helped someone up to speed. And yeah, you can feel free to send me a message. You can find my email. That's xen at Papa Alpha 0 Juliet Charlie X-ray.nl. And yeah, that's it. I will end it, and I will leave this video. I'll leave it online and for future reference.